Okay, this is the video lesson for Algebra 1, Section 4.3, Patterns and Nonlinear Functions. So the objective here is to identify and represent patterns that describe nonlinear functions. So linear, remember, is a linear function, a function whose graph is a non-vertical line or part of a non-vertical line. So there we go. And then a nonlinear function is a function whose graph is not a line or part of a line. It's like a parabola, or this is a third degree, this is absolute value. So we're going to look at patterns and functions that do not form a line. So let's look at this first example. We're talking about the area of a pizza. So they're saying it's a function of its radius, and the cost of the sauce for the pizza is a function of the weight. Okay, sorry, the area of the pizza is a function of the radius, the cost is a function of its weight. In ounces of the sauce used. So graph these functions shown by the tables below. Is each function linear or nonlinear? So that will require just doing a little graph here, and I will do that on pause here. So I'm just going to plot each one of these points. Doing the graph here, you know, you have your x-axis and your y-axis. This is all positive, right? Our radius is going to be positive and our area is going to be positive, so we're going to be in quadrant 1. And then since this is our independent variable, r, radius, that's going to go on the bottom. We have to make sure we can go from 2 to 10 here. And then the area is going to be our dependent variable, and that has to go from 12 to 314. So I'm going to scale this so that we can make sure we can hit all those. Okay, and then I chose to do this by 2s to go just to 10. That's easy. And then here I wanted to make sure I could at least get to 300, so I split these up by 50s. So this first one is 2, 12 is about here, 4 to just about 50, 6 is 113, so somewhere like here, 8 is a little bit more than 200, and then 10 is where we hit this 314, which is kind of here. So you can see it's not linear, right? It's not going up by the same each time. Okay, and then let's do the sauce. All right, and here we can set up the the W the same down here, and then here I just made each one $1. So then 2 is 80 cents, a little bit less than $1. 4 is 160, a little bit more than 150. 6 is 240, and look, this one's going to be linear. It's $4, yeah. If this is better scaled, but you can see that this is it's going over and up the same. Okay, but this one is not, right? This is going over the same, but not up the same. This is going up even bigger, and this is going up even bigger. So this is nonlinear, and this one is linear. All right, and that is why, right, as this changes by 2, this goes up. Actually, let me show you this using the graph. So you can see here, if your independent variables are all going up by the same amount, these are all going up by 2. And then how much are those changing? You can take your 50.27 and subtract the 12.57. And see, right, this is going up 37.7. Then if you do 113 minus 50.27, this is going up 62.83. So since these are constant, these are not constant, this is going to be nonlinear. So we can do it without graphing too. I think this example wanted us to show it with graphing, but that's what I'm showing. I want to show here, right? This is the 37.7, this is the 62.83, and then it's even more here. Once you have that 2 are not the constant, and you're just looking for linear, nonlinear, you can see this is nonlinear. And then this one we can see is going up also by 2 each time. So this is constant, right? Or let me just write this here so you can get it. This is, right, these are constant, not constant. So nonlinear. These are constant. Oops, let's not make that big mark. These are constant. And then these, they're going up by 80 cents each time. Right, if you take 240 minus 160, you get 80 cents. You do 320 minus 240, you get 80 cents. So this is going up by 80 cents each time. This is also constant. since they're both constant, it's linear. And then you can also see that in the graph. This is kind of going like that. It's kind of like a parabola. Okay, so time to try one on your own. So here is a table, shows the fraction A of the original area of a piece of paper that remains after a paper has been cut in half n times. Graph the function represented by the table. Is the function linear or nonlinear? So press pause, try this on your own, do graph it. It's just one graph, and then see if it looks like it's making a line. And then you can also test it by testing your x and then your y and seeing if they're both constant to be linear. Okay, press pause and then check back for your solution. Okay, so by the graph, you can see here, it is not a line. It's nonlinear. See, it kind of loops down like that. And then if you checked the x's or the independents, go up by 1 each time. And so they're constant, but the y's or your dependent variables do not go down by a constant number. So these are nonlinear. Or in the graph, you can see it is also nonlinear. Okay, moving on, we're going to look at a pattern. So this is talking about the total number of blocks in each figure as a function of the number of blocks on one edge. So what is the pattern you can use to complete the table, represent the relationship using words, an equation, and a graph? So in this example, we have, there's one block on the edge, but there are one total number of blocks here, right? So 1 to 1. So the ordered pair would be 1 and 1. In this one, the number of edges here is 2, right? And the number of blocks, though, is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 blocks here. Okay, and then when the edges, there is a 3, right? There are 27 of these blocks here. So here's our ordered pair. So what's the pattern? Right, you can see 1 becomes a 1, 2 becomes an 8, 3 becomes a 27. Right, this is 1. This is actually, these are making cubes, so it actually is the word cubed kind of helps us here. 1 cubed equals 1, 2 cubed equals 8, 3 cubed equals 27. So this was probably going to be 4 cubed, and this is going to be 5 cubed. And so the 4 cubed is 64. So this ordered pair is 464. And then 5 cubed is 125. So this ordered pair is 5, 125. Okay, so we use the pattern to complete the table, and the pattern, we want to represent the relationship of this pattern using words. And let's do the words first. Words. Now what you want to do is, for these, just to have some kind of system, is you can say, right, this, we can actually, let's do the equation first, just to kind of get us here. This is y, this is x, and we can see here, this is my x. X gets cubed, x gets cubed. So my y is x cubed. So the equation is going to be y equals x cubed. So when we put this into words, you're just going to say, just turn your y into words here, total number of blocks. The total number of blocks, you're just going to rewrite this equation, is equals is the number of blocks on edge cubed. All right, you're just like turning this equation into words. The total number of blocks is the number of blocks on edge cubed. And then you can do that as a system, maybe change the words to be more clear for you. You just, you cube the number of blocks on the edge to get the total number of blocks or on something or something like that. But I think it's good to have a system. If you have an equation, just turn the equation into words. Okay, so we did words, we did an equation, and now we need to do a graph. And so this is going to be, we need to get up to 125. So let's make this 125, and let's just split it into 2. 125 divided by 2 is 62.5 divided by 2. 31.25 divided by 2, and this is 15.625. Okay, and then we have our 1, our 2, our 3, our 4, and our 5. So this doesn't have to be perfect. 1 is really close to the bottom there. 2 is 8, that's just about less than half. And then 3 is 27, so a little bit less than that. 4 we get 64, so that goes up here. And then 5 we get to 125. So you can see this is like really getting up there. So this is nonlinear, obviously, in our graph, and we just need to show a graph. Actually, we knew it was nonlinear, right? Because it's the x cubed. Okay. So now there's one to try on your own. This table shows the number of new branches in each figure of the pattern. What is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. So see if you can figure out the pattern, fill in these two spaces here. What am I calling that? Sorry. Come up with an equation. First, I think that's easier. Turn that into words and then graph it. Press pause to do that and then check back for your solution. Okay, so figuring out this pattern isn't that easy, but it is just playing around with it, seeing, right, 1 times 3, 3 times 3, 9 times 3. You just keep multiplying by 3 each time. Maybe you noticed that, right? Times 3 times 3. So these are going to be times 3. So this is 3 to the 1 power to get you 3, 3 to the 2 power to get you 9, 3 to the 3 power to get you 27. So you can see this is my x, right? My 1, my 2, my 3, that's what changes. So that's where that x goes. That's how you kind of figure these out. So that's where our equation, y equals 3 to the x power. And then to do words, just turn the equation into words, which is number of branches is 3 to the power of the number of the figure. That doesn't really make sense in words. So I changed it to say, right, number of branches gets multiplied by 3 for the next figure. Maybe you come up with something better. My words are not great there. And then here's your graph. And you can see that it's nonlinear. Okay, and then these ones were just coming up with an equation, or what is the rule that represents this function? So here we're going to put this into the ordered pairs. You can put them into the tables, right? My x's, 1, 2, 3, 4, 5. My y's are 2, 4, 8, 16, 32. And then you're just going to look for a pattern. What can I plug 1 in to get me a 2? Then I can plug that 2 into the same spot to give me a 4. Plug that 3 in to get me an 8. Well, this is making me think, right? Times 2, times 2, times 2, yeah, times 2. And this is going to look just like that other one, right? This is, if you have it times, that's going to be your base of an exponential function. So 2, 2, 2, 2, and this is 2 to the 1 power, 2 to the 2 power, 2 to the 3 power, 2 to the 4 power, 2 to the 5 power. So, right, this is my x. That's what changes. So 2 to the x is my rule, or my function. All right, you just got to play around with it and see if you can find the pattern. And my hint, right, if it is multiplying by the same number each time, that's going to be the base of your exponent. It's probably your exponent that's changing. That's going to be the x. And you can just try those things out. So, speaking of trying, press pause, try this one on your own, and then check back for the solution. Okay, this one was maybe a little easier, maybe a little harder, because it didn't multiply by the same thing every time, but maybe you notice it's just, this is now the base, right? The base is what changes, but the exponent stays 2, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and this is what changes. The base now changes, so this is my x, right? If this is my x, so it's going to be x squared. Okay, time for practice. Enjoy.